All right, I'm going to be talking about section 2.7, related rates. Before we begin, it's important that you have your video notes, worksheet. I'm not going to be writing these problems on the board, so it's important that you have this so you know what I'm talking about. I'll be referring to these problems here as we go through this. Okay, before we begin, let me just say related rates are classic calculus problems. Students do find them difficult. They are sort of word problems, but you know, with some practice, they tend to get a little bit easier. But at first, just realize that these are going to seem very, very different than things we've seen in the past. Okay, so right here I have kind of a recipe for solving related rates. It tends to work. It tends to focus how we're going to do this. So definitely get these down in your notes. So step one. Take an inventory of known and unknown variables and constants. And when we work through our first problem, I'll talk about what these all mean. We're going to use proper notation here, derivative notation, etc. But that's a very important step. So the first thing is read the question, look at the things that are giving you and what we're trying to find. Okay. The second thing we're going to do here is we want to link the variables in question using one or more static equations. Static equations being like sort of standard equations that are sort of frozen in time, and we'll talk more about that. Today we're going to be using a lot of actually the Pythagorean theorem, a squared plus b squared equals c squared. So these tend to be pretty standard geometry equations. There are problems that we're going to see at some point where they actually give you this equation. That makes things a little bit easier here. And most of the ones we'll be talking about will have one equation that links everything together. Occasionally we'll see some problems where you have to take one equation to get this quantity, which then gets used in another equation. But for right now, it really is going to be one, and all the ones I'm doing today will be one equation. The third thing is we're going to take the derivative of each variable in terms of t being time. We do this through the process of implicit differentiation. The difference from the implicit differentiation we did in the past is, in the past we had x's and y's in our equations, and x was the independent variable and y was the dependent variable. So in those particular cases, we sort of took the derivative of x like we normally do, where if we took the derivative of y, we always use chain rule, thus generating a y prime. Today, when we do related rates, t is the dependent variable for all of these things. And basically every variable in the problem is going to be a dependent variable. So we have to use chain rule on all our variables. Even if we called something x, we would use chain rule on that. So this is a little bit different than what we've seen in the past. But the mechanics you're going to find are very similar. Once we do that, basically, from there, we're going to plug in the things we know, and then we're going to solve for the unknown variables and then answer the question. Okay. So these four steps basically will sort of streamline the way we approach it, kind of focus our approach as we solve these problems. But you know, these do tend to be difficult. I will tell you that what makes them typically difficult is step 1 and 2. Once you get step 1 and 2, as long as you know the calculus from there, they tend to fall out. Okay. So take a moment to copy these down if you haven't already, and then we'll begin on the worksheet with the first problem now. Okay, so now we're going to refer to the first question on our worksheet. So a ladder that is 25 feet long is leaning up against the wall of a house. So let's draw a picture of that. Okay, so we're always in these types of scenario going to assume that we're talking about a 90-degree angle. So this is the wall of the house, this is the ground, this is our ladder. Now the ladder in this case, and one of the things that's very important is we keep track of what's a constant. It stays the same throughout the entire problem, and what's a variable. Those things can be quite confusing, and really we want to establish that at the beginning because it's really going to drive how we do the problem. So the ladder leaning up against the house is 25 feet. That's never changing, so we want to mark that down now. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. So what's happening is this ladder is sort of sliding out here. Now, what that means is this is changing. So this we want to enter as a variable, and I'm going to use x, and typically, you know, if I'm thinking the horizontal axis or the horizontal dimension, I'll typically call x. Now, as this slides down, okay, this quantity here is decreasing, so once again, this is a variable. So it's very, very important we establish what's a variable quantity, and I'll talk about sort of the pitfalls of that later. So now at this point we want to start taking our inventory. So once again, the base of the ladder is pulled away from the wall at a rate of 2 feet per second. So as soon as we're talking about a rate, so this is sliding out here, we realize that x is increasing. So we're going to label this as dx over dt. Don't just call it x prime, because we want to show that t is the independent variable here. In all of these problems, t is going to be the independent variable, and this is going to be 2 feet per second. Okay. If the ladder was being pushed up against the house and x was decreasing, we would make this a negative. So something you want to keep track of as you do these problems is your rate of change negative or positive. And the way we determine that is the variable increasing or decreasing as the system moves on. Okay. And then finally, we're going to go through each one of these parts, which is going to be different for each part. So this is the general situation, but we're going to be asked different things for A through C. So part A, how fast is the top moving down the wall when the base of the ladder is 7 feet from the house? Okay, now here's the deal. So we want to know how fast this is moving down. All right. Now I already know that this is going to be a negative. So in other words, what I'm interested in here is I'm interested in dy over dt. This is what I want to find. And this is what I would call the inventory. Now the next thing is, you'll notice this phrasing, when the base of the ladder is 7 feet from the wall. So that's when x is 7. Now here's the thing, the most common mistake that people will do is right away they'll plug that 7 in for x. We do not want to do this. This is what I call a snapshot. X is moving in the scenario, it's a variable. But we're interested when, and that's a key phrase with these snapshots, when x is equal to 7. So the way I sort of kind of section this off is I put, you know, for snapshot, x equals 7, and that's feet. And it's very important that we do our calculus first, then plug that in. Otherwise, we'll lose quantities that are important to us. Okay? Now, what we want to do is we want to link our variables in question. So let me point out to you that we're given information about x, and we're asking a question about y, dy over dt. So I want to link, so by the way, if you're looking at that recipe I gave you at the beginning of this video, this is step 1, the inventory. Step 2, we want to link the variables in question. So once again, they're asking me, they're giving me information about x and dx over dt, and they're asking a question about dy over dt, so I want to link them. Whatever geometry formula is going to link them is what we want to use. So here, since we're talking about a right triangle, we're going to link these using Pythagorean theorem. So I'm going to say x squared plus y squared is equal to 25 squared. And this is definitely an open calculator problem, but really just for the arithmetic here. Okay, so that's step 2 done. For these problems today, as I talked about, we're just going to be using one equation for each. So step 3, this is where I do the calculus. I'm going to take the derivative of this equation implicitly, okay? The difference here is that t is the independent variable, which means all of these variables I have to take the derivative using chain rule. So this looks like this, 2x, and then I'm going to call this dx over dt. Don't just use y prime. I want to show that I have this other variable here, t, which is time, and this other one will be 2y, and then dy over dt. And notice there's no point in figuring out what 25 squared is, because I'm taking the derivative of a constant, that's going to be 0. Now, if I want to make my life a little bit easier here, I can cancel out the 2's and call this x dx over dt plus y dy over dt is equal to 0. So that's step 3 done. Now we're on to step 4. We are going to go ahead and plug in these snapshots. So let's be clear, any snapshots, and the key word there is when, we want to plug that in afterwards. If I plug that 7 in the front of this, then I lose that rate of change. So if you get in a scenario where all of a sudden you're missing rates of change you need, you probably plugged in your snapshot before you took the derivative, before you did the calculus. Okay, so let's plug this in. We have 7. We have dx over dt, which is positive 2. We'll worry about the units later. Plus y, we need to figure out what the snapshot for y is, and I'll talk about that in a moment. And then dy over dt is ultimately what I'm trying to solve here. Okay, so now y, we're going to use the static equation, and this is pretty common. So when x is 7, what's y? So we have 7 squared plus y squared is equal to 25 squared. So for this, we'll just grab our calculator. If these are in a closed calculator context, as I talked about, I tend to be pretty kind to you with the arithmetic. And we will definitely see these in a, so let's see, is there a square root of this? Okay, so what we get is a snapshot of y equals 24. And we want to hold on to this because we'll actually be using this later for some other questions. Okay, from here it's just a matter of solving this algebra 1. This is just like if we had x here. So from here I can just go dy over dt is equal to, we can move that over here, so that would be negative 14 over 24. You know, we can go ahead and simplify this here, so that would be negative 7/12. And then our units, these once again will be our linear units, so this would be feet per second. As I talked about, the reason why that's negative is because y is decreasing over time. Okay, so that's part A done. So once again, let me go through it. Step 1, you take the inventory, all the things that they're giving you, what we know and what we're trying to find out. Step 2, you link those variables in question. And step 3, we take the calculus. And step 4, we solve. Okay. All right, so let's move on. The problem situation is going to stay the same, but they're going to ask for different quantities here. So I'm going to go ahead and erase, and then I'll pick up here on part B. Okay, part B. So consider the triangle formed by the side of the house, the ladder, and the ground. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. So once again, they're going back to this snapshot. So that's why I said this y value we're going to end up using again. So now they want us to talk about the rate of change of the area. So what we want to find here, so this is the inventory. We still have this information from before. We want to find what dA over dt is. So I want to link these variables. So this is pretty straightforward because it's just a standard right triangle. So the base of that triangle will be x, the height of that triangle will be y, so my static equation. And what you're going to find is usually static equations are not so bad. 1/2 base, which is x, times y. Okay, so that's our static equation, that's step 2. Now step 3, we're going to do the calculus. We take the derivative of each variable with respect to time again. So we do have to use product rule here. So the derivative of a is 1 dA over dt. Okay, we want to write d over dt, don't want to see that a prime in this context. And now we're going to use product rule. So the derivative of 1/2 x will be 1/2 dx over dt. X is also a dependent variable, copy down the y, plus, now take the derivative of y, so that'll be 1/2 dy over dt, and then x. Okay, once again, just like before, you know what, I take that back. This is fine, we'll leave it as is. Okay. So now what we're going to do is we're going to plug in our snapshots and solve what we're looking for. In this case, is dA over dt. So 1/2, our dx over dt is 2. Yeah, 2. Our y snapshot here is 24 plus 1/2. Oh, and then dy over dt, we actually calculated, because they're using the same snapshot as before, the dy over dt is the same. So we're using that from before, so what was that? Negative 7/12, yeah. And make sure you have the negative there, otherwise they'll throw this off. And our snapshot for x is 7. Okay. Okay, so let's see, let's do a little simplifying here. There's not a whole lot I can do though. So this will cancel with this. and I'm going to get 24 minus 49 over 24. You know what, I'm just going to go ahead and change this to a decimal. Remember, if we are using decimals, we want accuracy to 3 decimal places. Okay, we could get a common denominator 24, but I'm not too interested in that at the moment. So let's just grab the old calculator. And what we get is 21.958, and then 3 repeats. And as long as you're accurate to 3 decimal places here, you're going to be fine. Now, what are our units? So realize it's dA over dt. So we want to think about what the units are for area. So the units, since we're talking about feet, will be feet squared, and that's per second. So that is our dA over dt here. Okay, so let's move on to part C. I think I can fit this in here, hopefully. Find the rate at which the angle between the top of the ladder and the wall of the house is changing when the base of the ladder is 7 feet from the wall. So once again, we're going back to that 7 feet snapshot. So they're talking about this angle here. I'm going to call this theta. You know, that's a pretty common variable we'll use for angles. So we want to link this. Now, we actually have all sorts of options here in linking these variables. So we want to find d theta over dt. Sorry, going a little bit quick here. This is what we want to find. Okay, so we want to link theta to any of these things I already figured out. So I can use any of the SOHCAHTOA trig properties I want. So really anything. What I'm going to do is I'm going to link what's going to give me the easiest derivative. And the easiest derivative in this case is going to be y on top, 25 on the bottom, because it's a constant. If I did something like tangent of y over x, when I take that derivative, I'm going to have to do quotient rule and things like that. So it's going to be a little bit annoying there. So I'd rather just do a standard power rule type derivative. And if I use sine, I'm going to be able to do that. So if you're not conscious of what's going to make this the easiest, that's okay. Any right triangle trigonometry trig function will work, but sine is definitely going to be the easiest. So sine is going to be y, sine of theta will be y over 25. Now, because I'm going to take the derivative of that, I don't want to leave this as a quotient. I'm going to call this 1 over 25 and then y. Okay, so now when I take the derivative, this is really straightforward. So this will be cosine theta. The derivative of sine of theta will be cosine theta, but then we got to take the derivative of theta. Every single variable we got to do chain rule with related rates. So that will be d theta over dt is equal to 1/25, and then this will be dy over dt. Okay. I can almost fit this all in here. So cosine theta, now a lot of people will go, okay, so I got to figure out what theta is. You actually don't. We have all our snapshots here. So let's write our snapshots here so we understand what's happening. Our snapshot for y is 7. Nope, it's not. I have these flipped. Our snapshot for y is 24. Okay. Our snapshot for x is 7. Okay. What I realize is, and then this is always 25, so that's a constant. So cosine, I'm just doing from theta adjacent, which is 7 over 25. So I don't actually have to find out what theta is because I can replace that whole cosine here. So cosine of theta is equal to adjacent over hypotenuse, so that's going to be 7 over 25. So that's our cosine. And d theta, all right, let me give myself a little room here, so I'm going to erase a little bit up here and start over at the top. Okay, let's continue on with C. So we're going to go here, and then our next line will be up here. So not necessarily the most organized, but I think you can deal with it. So once again, as I was saying, the snapshot for cosine theta, we can replace that whole thing with adjacent, which is 7 over hypotenuse, which is 25. D theta over dt is what I'm trying to figure out. And that will equal 1/25. And then dy over dt, we found in part A, that's negative 7 over 12. Okay, so d theta over dt is equal to 1/25, we'll move the negative out front, times 7/12, and then we're going to multiply by the reciprocal here, so this will be 25 over 7. So we see the 25 cancels and the 7s cancel, so that's 1, that's 1. So what we get is negative 1/12. And our units here, we're talking about measurement and angle. In this class, unless it's a really, really uncommon event, the units that we're going to use always for angles is radians. So this will be radians, and that's per seconds. So that is our d theta over dt, and that is problem 1 done. Okay, so let's move on to problem 2. Okay, problem 2, this one's going to be a lot quicker. Air is being pumped into a spherical balloon at a rate of 4.5 cubic inches per minute. So realize cubic inches, we're talking about volume of the balloon. Now we're talking about a spherical balloon. So cubic inches per minute, we'll call this dV over dt, and this is 4.5 cubic inches per minute. Find the rate of change of the radius when the radius is 2 inches. So we want to find the rate of change of radius, we'll call that dr over dt, okay? And when the radius is 2 inches, so once again, that word when should set off bells and whistles. That is not something I'm going to plug in directly. That is a snapshot that goes in after I do all the calculus. So I want to label that snapshot, and r is equal to 2 inches. So just kind of keep that aside for after I do the calculus dealing with the problem. Okay, I will tell you that the formula, so just so we're clear, we're given information about volume. We're asked a question about the radius of a sphere. That's not a formula you have to memorize like Pythagorean theorem. This is something that would be given to you if you needed it. And the formula here is V equals 4/3 pi r cubed. Okay, so we have exactly what we need because this perfectly links V and r. Okay, so now at this point, I can take the derivative of this. So this would be dV over dt. The 3 will come down. Treat this whole thing as a constant because it is a constant. The 3's will cancel. I'm left with 4 pi r squared, and then that's going to be dr over dt. Key to related rates is always keep in mind all these variables move with respect to time. Okay, so in dV over dt, we know that that's 4.5. So this is step 3. We're plugging in our snapshots. R is 2. So that would be 2 squared, and what we want to find is dr over dt, that's our unknown. So let's see, that's 4 times 4, that's 16 pi, so we get 4.5 over 16 pi, and the units here for dr over dt will simply be inches per minute. I don't want to leave it like that. I really am not a big fan of decimals mixed with fractions. It's right, it's just somewhat problematic. So I have a couple options here. I could call this 9/2. I could make this 9 over 32 pi. That's one option. Or I could just plug this in my calculator if it is open calculator. There's nothing wrong with that. So that's divided by 16 pi. And we would get 0.0895, and you just have to be accurate to 3 decimal places, either truncated or rounded, and that would be inches per minute. So that's that whole problem there, pretty straightforward. Okay, so let's move on to problem 3. Okay, problem 3, they give you a drawing here. Please forgive my crude drawing of a plane. Looks more like a person, I suppose. But anyways, we have an antenna here, plane flying over, the altitude is 6 miles. So the question then goes, when the plane is 10 miles away, okay? So that is, once again, our snapshot, and this is the antenna. And the antenna does not track the horizontal distance, it's just the distance from the antenna to the plane. So it's always going to be this hypotenuse here. So when that is 10 miles, S is changing at a rate of 240 miles per hour. In other words, ds over dt is equal to 240 miles per hour. What is the speed of the plane? So understand, if we're talking about the speed of the plane, we're talking actually how fast x is increasing here. So this is going to be dx over dt, and that is what we're trying to find. Now the 6 miles, the altitude of the plane, we're going to take that as a constant. Of course, in reality, there'll be slight variations, but we're basically going to be the same that entire time. Okay. So now what I want to do is I want to link the variables in question. So I'm given information about S, and I want to link that to dx over dt. So we're back to Pythagorean theorem. And I will tell you, this is a pretty common thing. We saw this on problem 1, part A, and we're seeing this again. So x squared plus 6 squared is equal to s squared. Okay, now we take the derivative of each with respect to t. So this would be 2x dx over dt is equal to 6 squared. Doesn't matter what that is, that's a constant. You take the derivative constant, you're going to get 0. And this is going to be 2s ds over dt. Okay. Notice that the 2's can cancel here. So this will be x dx over dt is equal to, make sure my s's don't look like a 5, s and then ds over dt. One of the trends I've been trying to sort of get you to realize is we want to simplify when it helps us, but we don't have to simplify. Only if it makes our life a little bit easier here. Okay, now as I start to plug this in, I realize, first of all, I need to figure out a snapshot for x. So I have dx over dt is what I'm looking for, so that's going to stay a variable. I have a snapshot for s, that's 10, okay? And we have the ds over dt, which is 240. Okay, but I need to find a snapshot for x here. So I'm going back to my original equation. That is a pretty typical thing here. And we're going to plug in, so we have x squared plus 6 squared is equal to 10 squared. Okay, so x squared is equal to 100 minus 36. So that's 64, and it just so happens that it is a perfect square. So our snapshot for x is 8, and now from here, dx over dt is equal to 10 times 240 over 8. And so let's see, 2,400 divided by 8. And we get 300 miles per hour. And that is dx over dt, which in this case is the speed of our plane. Okay, one more problem, problem 4. Problem 4, the radius of a sphere. So once again, we're talking about a sphere, so volume equals 4/3 pi r cubed is likely to be our static equation. Okay, so the radius of a sphere is increasing at a rate of 2 inches per minute. So that is dr over dt. So this one's backwards than one we saw in problem 2. In problem 2, we were starting knowing information about volume and getting r. Here it's the opposite. We're getting information about r, and we're going to want information about v. Okay, so we have 2 inches per minute. Now, in this case, and then ultimately what we want to know is dv over dt is what we're trying to find. Notice there's 2 different snapshots here. And really the point is what we're going to see is this system is dependent on what the snapshot is. dV over dt is changing. It's not constant. Okay, so when R, even though dr over dt is constant, that does not mean that dV over dt is constant. So let's do the snapshot. So there's going to be two snapshots. So when R equals 6 inches. So that's our first snapshot. So the derivative of this, dV over dt, 3 comes down, cancels with the 3, 4 pi r squared, dr over dt. This is going to be the equation I use for both. So now let's plug in our information. We want to know dV over dt, okay? That is 4 pi 6 squared, and then dr over dt is 2. Okay, so we're getting 2 times 36 times 4. So that's 288 pi, and that is going to be inches cubed, because we're talking about change in volume over minutes. If you want to use a decimal, just make sure it's accurate 3 decimal places. I don't particularly care. So that's the when R is 6 inches. Now let's look at when R is equal to 24 inches. Okay, so dV over dt, we're still using this formula, is equal to 4 pi. R is 24, it's right in front of me. So that's 24 squared, and then dr over dt is still 2. That's a constant. Okay. So 4 times 24 squared times 2. So what we get here is 4,600, and that's a comma, not a decimal point, and that's inches cubed. Pi, and that is inches cubed per minute. So we can see that actually when we went from R is equal to 6 to R equals 24, our volume is increasing much faster. A lot of times in these systems, people will make the wrong assumption that if one rate of change is constant, they all will be constant. That does happen sometimes, but most of the time there is some variation when we see these problems. Okay, so obviously I threw a lot at you here today. Let me just tell you, this is something that we're going to have time to work on problems in class and digest over the next few periods and even perhaps weeks. Okay, so that is 2.7 related rates.